Okay, 102 students, let me try another one. I got a question here from back in chapter 7. But chapter 7, number 15. And again, remember the main point of this particular chapter is about conservation of energy. And so if we take the energy before, it is equal to the energy after. So in number 15, it starts off, it says a baseball, and then they give the mass of 145 grams, and it's thrown straight upward with a kinetic energy of 8.7 joules. So maybe if I just, set equals, and I say, okay, so there'll be some initial kinetic energy. And it sounds like they're giving me that number, 8.7 joules. Okay. Then that's got equal to the total energy a little bit later. Now, where does it go? It says, when the ball has risen 6 meters, find the work done by gravity. So, in other words, when the ball goes upward, at some point upward, 1 meter, 2 meter, 3 meter, 4 meter, doesn't matter how far, it's going to have some kinetic energy, and then it's going to have some, what your author says, work by gravity. And that would be our force times our distance. And so in the case of gravity, gravity pulls on it with a force of mg, and it goes up a distance of h. So we called that the gravitational potential energy in this chapter. And so this would say that the original 8.7 joules is how much energy we have to work with. And as it goes up, it's beginning to get more of this and therefore less of this. So as it gains more gravitational potential energy, it then loses kinetic energy. Okay? And, right, of course, at some point, I suppose it will actually then lose all of its kinetic energy, come to a stop, which is why it would have its maximum height, and then it would begin to fall back down, losing its gravitational potential energy, but gaining in its kinetic energy. And I suppose when it got back to its same height, so height is 0, then we could say that its kinetic energy is the same as it started with. It's now just going down, but it's going with the same speed, just down, so it has the same kinetic energy. I suppose that we could even argue that it might even go lower than it was originally thrown. So that's a negative number, which makes then this number having to be greater than 8.7. So that means it's going even faster than it was when it's thrown up. Okay, but in this one, the first part of this is just asking this part of the question. This is A, how much work is done by gravity. So if we go mgh and we do the rounding to 10, let's see what we get. So the mass is 0.145 kilograms. G is roughly 10. Let's see what we get. We might have to do the 9.8, but it doesn't look like it. It looks like that if we do the 6 meters that they're saying it's thrown up, so 0.145 times the 10 times the 6, I get 8.7 joules. Yeah, that's kind of what I was thinking it would come out to be. So what this is saying then is you start with 8.7 joules of kinetic energy. And now that it has gone up, we should have less kinetic energy. And how much less depends on how much has gone into this term, the gravitational potential energy. And according to this statement, it is the 8.7. So when you subtract them, you're going to say that the final kinetic energy is 0. And of course, remember that equals to 1/2 mv squared. So that means the velocity is 0. So this is really saying it's at its highest point. Okay? And I think I just answered the other two. This is B. Part B then says, what is the ball's kinetic energy? Yeah, so if, again, essentially, if we had 8.7 and all of it went into potential, that means there's nothing left for kinetic. So there's B, which is 0. And then, of course, then C is telling us its speed. And so there's the answer to C. Its speed would be 0. Oh, good. All done.